All right, it's 3 o'clock. You guys think we should start? Got a lot of material to cover today, and we have an exam at the end. Thanks everyone for coming out today. I'm sure the weather wasn't quite nice enough for you to stay outside and enjoy your lovely Sunday afternoon. Instead, you're here with me, and I can torture you with mathematics. Yay! All right, I'm here to talk about mathematics and reality. I guess maybe introductions in order. Who the heck am I? Well, my degrees are all in maths and applied maths. I studied, did my bachelor's and my master's in applied mathematics in New Mexico. I don't know if maybe you can tell by the sound of my voice, I am not a Kiwi. Is there any doubt? Right? I am New Mexican, right? University of New Mexico. Also did a brief stint at Sandia National Laboratories, one of the big shot Department of Energy labs in America, working in the nascent computational biology department. And then I came to New Zealand to study with a big shot in mathematical biology at the University of Auckland, did my PhD studying calcium dynamics, calcium signaling inside cells. Did a postdoc at Auckland Bioengineering. Auckland Bioengineering! Yeah. And let's see, did some stuff with bioengineering. And then now I'm also working at Massey University. I'm looking at neuronal networks, which is a rather different kind of mathematics, but be that as it may, it pays the bills. Maths is fun. I've done a lot of lecturing over the years, teaching maths. Hi. And everyone I see, whenever I'm teaching maths, they say, wow, these questions that you asked are so easy. Yes, where is X? Oh, it's right there. Sweet, easy peasy, right? Also, it's like, can you simplify this expression? Well, you cross out the ends and you get 6 = 6, yay! Maths is easy, right? And so you're just following the patterns, right? What's the limit of this thing? Is X going, oh, it's 8 sideways. Okay, so the limit of this thing, it's 5 sideways. You see the patterns? Oh, the patterns, follow the patterns. Although I have seen some of my students express their frustrations in rather artistic ways. Maths can be challenging, don't you think? Right, and I'll just show you some of the maths that I've done. It's, these derivations that I went through for this was a paper that I worked on studying the influence of spatial communities and their distributions on malaria. And so sometimes you end up playing around with these beautiful, hideous expressions. And one word that kept coming to mind when I was working on this research was ugly. Ooh, so ugly. Thanks for coming, guys. So mathematics can be challenging. Mathematics can be ugly. So why do it? Why bother? There's a bit of mystery involved. Why do we do these things to ourselves? That's partly why in my PhD, my dissertation, I put in an excerpt from a piece of fiction, and I thought it was appropriate, and I'll just read that to you now. All golden and lovely, it blazed in the sunset with walls, temples, colonnades, and arched bridges of veined marble. Silver-basined fountains of prismatic spray and broad squares and perfumed gardens and wide streets marching between delicate trees and blossom-laden urns and ivory statues in gleaming rows. While on steep northward slopes climbed tiers of red roofs and old peaked gables harboring little lanes of grassy cobbles. It was a fever of the gods, a fanfare of supernal trumpets and a clash of immortal cymbals. Mystery hung about it as clouds about a fabulous, unvisited mountain. Mystery. Why bother? Well, we're human. We get curious about things. Why is it this way? Why does it work? That introduction was from one of my favorite horror authors, H.P. Lovecraft, the American author. His descriptory powers are quite fantastic. That was the beginning of this book and the dream quest of a fellow named Unknown Kadeth. Mathematics can be a mystery. Mathematics is also handy. Math is used by nurses to calculate how much drugs they give you so they don't kill you. Thank you, nurse, for not killing me. Right? Mathematics is used by builders to make sure a room is square, that the thing doesn't collapse, right? That's pretty handy. Oh. Is anyone afraid this is going to collapse at any moment? Because it didn't use maths? It's also handy for like, computing change, dealing with how much money you owe someone. I'm pretty sure everyone signed the form at the beginning. I owe Shawn $10 bazillion. Thank you. That's probably in play money, right? Play money. I'm going to tell you a little bit about some of the history of some mathematics. This is an excavated altar in India. It was apparently around the 2nd century BC. This ancient structure had very specific building requirements, very specific order in the way it was constructed, very specific geometrical forms, squares, rectangles, triangles. It had to be consecrated in order. It was very important to them that it be done right. Oh, thanks for coming, guys. Hey. This inspired some studies on how to make these triangular bricks just so, because it was very important to them. Okay, so how many of you thought you were going to come to a math talk and not do maths? You were wrong. Right, so consider, if you will, have you ever noticed that in math exams? Consider these two squares. Okay, this one's got a length side A, this one's got a length side B. Right? Thanks to the power of PowerPoint, I can shift these around. Ooh, how did he do that? I click this button. Right? And I can make a square out of this thing. It's got a side length A plus B. I can take these extra bits, cut them up. If we remove the original squares, I can take these extra bits whose lengths have A and B, A and B. I can rearrange these just with a click of a button. Isn't that neat? Moving them around, ooh, the power of my mind, right? But notice how it's the same square, right? I've just rearranged things a little bit. These were the original squares. They had areas of A squared, B squared, and the gray bits. Notice these are the gray bits. The stuff where I cut these into triangles, we can call that C. This length corresponds to this length, C. I can see I'm already losing some people. We're getting there. Hang in there. Okay. So this bit here, that's a square. What's its area? It's just C squared, right? C squared. So remember, I had originally these two squares. Now I've got this square, and I had the gray bits for the extra bits. Take away the extra bits. Stay with me. Stay with me. We're almost there. What have I just proven? A squared plus B squared equals C squared. So I heard some people say Pythagorean. That's ridiculous. This is the theorem of PowerPoint animations. Right. So you're all co-authors on a paper. We're going to publish this thing, and we'll be famous. Well, probably not. Yeah, there was this fellow Pythagoras, but there are others as well. There's some evidence that Babylonian mathematicians understood this formula ages ago, right? In 1800 BC. Mesopotamians, Chinese, the Indians, of course, and those fellows, the Pythagoreans, all independently came up with different proofs, encountered this in different ways. The so-called Pythagoreans, who were the first to take up mathematics, fancied that the principles of mathematics were the principles of all things. What do we mean by discovered here? Encountered, ran into, stumbled on, fell on their face and went, oh crud, there's triangles all over my face. Like they're going onto some strange continent, hefting a periscope and a rifle. Ooh, look at that. I see triangles, right? Or maybe they're inventing things like Tesla. This fantastic image of him sitting there reading the newspaper while gazillions of volts transmit over his head. What is mathematics? What are these things? Are we just making all this up? Sometimes when you want to know what something is, you know what you do? You look it up in the dictionary. What does the dictionary say? Oh, mathematics. It's an abstract science of number, quantity, space. Mathematics may be studied in its own right, pure mathematics, or is applied to other disciplines such as physics and engineering. Applied mathematics. That's what my degrees are in. But I would also add something else in Shawn's dictionary addendum, and relationships between them. Now, that's what a formula is. It's a relationship between two quantities, how one varies in a specific way and it changes the other one because they're related. Numbers, quantity, relationships. It's also a language of precision. See, the sum of the areas of squares besides the lengths of a right triangle's leg is the same as the area of a square of the side length of the same right triangle's hypotenuse. That's the leg opposite the right angle of the triangle. Did you get that? Yeah. Or simply a squared equals b squared plus c. That's a little bit easier to say that, right, for a specific triangle. But so why does this relationship, why does it work? What are we looking at here? What's going on with this weird thing called maths? Any Simpsons fans in the room? I'm not alone. Good. Okay, thank you. Thanks for sharing. Right, we, the Indians, the Chinese, the Greeks, the Babylonians, discovered this Pythagorean theorem, and just the term discovered implies they exist like a real thing in some abstract reality. Philosophers have wrangled with this for ages. So there's one version called Platonism, realism, that proposes that mathematical things actually exist. Mathematical entities have an existence independent of human minds. These entities inhabit a special world, some Platonic world. Like, I guess that's where Homer is right now. How do these Platonic entities, though, which do not have spatial or temporal characteristics, get in touch with the physical world? How do they interact with each other? There's another view. No, they're not real. They're fictions. They're anti-real. They're just imaginations. They have no existence in and of themselves. And this can be thought to include logicism. Mathematics is true within mathematics. Formalism, math is just a bunch of rules. And languagism, math is like English, but, well, not. But maybe a bit handier for things like a squared plus b squared equals c squared. Maybe it's just a game. Maybe it's true within the story of math, this logicism thing. Math is nothing but a systematic construction of complex deductive arguments. All of mathematics, including its axioms, postulates, could be derived entirely from logical laws. Some kind of logical game. A game with logical rules, nothing but a set of rules and formal manipulations of symbols and terms according to these rules. There are no meanings attached to them. Mathematics is just like a chess game. Huh. So it's like, does anyone play cards? Does anyone play board games? Settlers of Catan, Beans, Bonanza, that's a great game. So that's basically what maths is. That's what they're saying. Or it's just a language, a product of human imagination grounded in our experience with the world and functions like a language. Beginning with numbers along with some operations like addition, we can find an immediate link between human experience and the structure of the world around us and mathematics. We all have mathematical abilities, right? We all calculate stuff, right? You do sophisticated calculations every day. Did anyone drive here today? So I drove. Yeah. I feel ashamed. I should have rode my bike, but you know, I've got to put on weight, right? So when you're driving, you're doing vector algebra. Does anyone know that? When you're trying to pull out in front of traffic, do you see vectors? Oh, I'm gonna die. Right? That's what you're doing, right? No, you're doing these calculations. Oh, okay, you're going a little bit too fast. I won't pull out in front of them. But you are doing vector algebra. How does that make you feel? You're a vector algebraist, right? Or what about just playing ball? Tie, catch. I think I broke it. So what happens when we drop these things and they break and Shawn Means in front of it? Well, we have an expectation, right? So if I throw you a ball, what's the trajectory of the ball? Is it random? Is it purely random? Does it go? Right? Hey, Adrian. So it follows a specific trajectory that you expect to see. Oh, it still works. Okay, we're good. Right? Also, how many calculations have you done to avoid a math exam? How many can I get away with? I'm sure if I tell them my fourth grandmother died, etc. Bloody casts are pretty convincing. Just a handy tip. All right. Our encounters with the logic causal reality we live in is suggested as key to our abilities for mathematical discovery. Indeed, we have innate cognitive abilities that are well suited to interaction in a world that has a logical structure. Right? Friction, gravity, inertia, all these things that we live in, we learn how to interact with. Right? These have all become genetically fixed in a course of evolution, according to one perspective. We do live in this environment, exhibiting properties such as cause and effect, relationships between force and action, consistently measurable quantity, extent, and evolution is proposed as the mechanism creating this ability. The logical schemes and hypothetical representations are the same as the logical schemes and coordination of actions, schemes that have been tested through eons of evolution and by now are genetically fixed. In other words, math is no different than calculating when to pull on the motorway. Do you buy that? That sounds like a death knell. No. Driving and deducing are the same thing. I'd like to tell you a story. Can I tell you a story? I like telling stories. About Bob the mathematician. When I was at Sandia National Labs, I was in the mathematics, computation, computers department. And there was this fellow, Bob. He was this brilliant mathematician. And I would see him and I'd say, Bob, what are you doing? Oh, polyhedral combinatorics. Okay, Bob, bye. Bob was very smart. But Bob was not the most socially skilled or the most practically minded of fellows. And we would all share Bob stories. Like, Bob asked me out to lunch today, and you wouldn't believe what happened. Oh. But I'm going to tell you specifically, hey, Josh, about a particular time when a Bob story appeared to one of the sysadmins in the department, one of the computer administrators, right? He's like, oh, I got a Bob story for you. You wouldn't believe what my day has been like. Oh, what happened with Bob? So it's like Bob came into my office, and Bob asked me, do you know anything about the wheels on cars? Oh, a little bit. What's wrong? Well, they don't seem right. Can you come and look at the wheels of my car? It's a little out of my job description, Bob. But okay, so he goes out, and this is what he saw. The tires have been destroyed, and the wheels were damaged because he'd been driving on flat tires for goodness knows how long. So it's like, Bob, did you notice anything was wrong with the wheels? Yeah, it seemed a little bit wrong, but I don't know. So it's like, well, I gotta get new tires. He goes, can you help me? I don't know what to do with that. It's not really in my job description, but okay. So he took Bob, got the car fixed, got him new wheels and tires and all that, and then he went back to work and shared with everyone his story about Bob. This idea that driving and deducing are basically the same forms of logical reasoning conflates two very different ways of thinking. Sure, we can do sophisticated calculations. We may not see the vectors flying around us when we drive on the motorway, but it's a distinctly different thing to drive and do abstract deductions. Very different ways of doing things. One of the oddities of human intelligence is that its level of advancement seems like a case of overkill. These higher intellectual functions are a world away from survival in the jungle. Most biologists believe the human brain has changed little over tens of thousands of years, suggests that higher mental functions have lain largely dormant until recently. If these functions were not explicitly manifested at the time they were selected, why were they selected? How can natural selection operate on a hidden ability? The evolutionary perspective runs into some problems on dealing with these issues, right? Okay, so consider a square after all that. So you ready for some more? I can see some of you are already bracing. Oh, okay, the eyelids. Come on, we can do this. Calculate stuff. Okay, so I give you a square. It's got a side length x. What's the area? Very good. Okay, so I can make a table, right, of values. Inputs, outputs. I have a relationship, right? So the area is a function of the length of this thing, right? Very straightforward. And I can also plot it, because we like plots. So visually, you can see how the area varies as a function of the side, right? Okay, so I can ask you, what side length gives us 0 area? 0. Why? Why do you say that? Well, it's because of what it says. What's the area? It's 0, 0, 0. You can also see it on the plot, right? You can just, it's right there. It's where it crosses the x-axis. Right, so visually we can process this and we can answer the question. We can also do it analytically. We can just solve x squared equals 0. 2 nothings is nothing. Yay, we did some maths. Yay, let's go party. Right? Okay, sweet. We can also plot this out It's a negative length, right? So I can say, oh, if my x is minus, it squares and I get positives, right? But so wait a minute, what's that saying? I have a negative length? What's negative length mean? So I dropped off at miter 10 and I went into the black hole department and I got my negative length tape measure. Negative length! Yeah. What does that mean? What is negative length? It falls out of a black hole. There's no meaning to it, right? So do we just reject negatives altogether? Negatives have no meaning, have no value. These numbers just don't make sense. Well, until you get into debt. Right? Or until you go underwater, or it's freezing cold. Right? So there's context that adds meaning to some of these things, right? Even though negative length doesn't make sense, right? They still have a meaning within their context. But so for this particular model of reality, we say that the negative lengths don't make sense. So this is where the model is valid. And this all comes from, does anyone remember this stuff from primary school? Let's see, how do I get a negative sign out of multiplying stuff? There's lots of whispering. Let's say, okay, 1 times 1 is, minus 1 times minus 1 is. You guys seem so uncertain. Let's see, 1 times 1. 1. Okay, minus 1 times minus 1. 1. Minus 1 times plus 1. Minus 1. Okay, sweet, we got it. Sorry, we're torturing you with math on Sunday afternoons. All right, but so this is a lot because we have these basic rules for multiplying signs, right? The very idea, though, of negative numbers was not accepted until about the 17th century. Imagine that. It's almost because there was no context, right? It's like, well, this doesn't make sense. So they're just not real. They don't exist. So let's just discard them. But so having negative numbers gives you a bit of flexibility in doing things. Let's say we have another square, length side 1, whose area is 1. And there's a tax. IRD says, I'm going to charge you an area tax. So however much area you have, you pay an area tax of 1. And the tax man will be along shortly to carve it out of your eye. Thank you, tax man. We love you. So I can do the same thing, right? So I have my inputs, the length of my x, paying my tax. I have my outputs. I can plot this thing, right? And I can ask the question, what side x breaks us even with IRD? How much area do I need to begin with to pay my area tax? Well, it's intersecting here where it's 0, right? I can solve the thing. I can say, where is this equals to 0? So if my area is what, I can pay my area tax of 1. It's amazing. I can ask a math question and people just, whoop. I don't want to say anything. So if my area is 1, if the side length is 1, 1 times 1 is 1, minus 1 times 1 is none. So I break even if I have an area of 1, right? You buy that? Are we on the same page? Okay, because I know I've got some math people in here, and they're looking at me, doing it wrong. Okay, so what if I flip this around and I say this is now a refund? So this is what IRD is going to come around. Here's your 1 area. Here you go. Enjoy. Have some area. Okay. We can do our table, right? Start off with side length 0. Oh, we got a bonus area 1, so that's our final area. Right? I can turn around. I can plot this thing. So this is the final area that we get. Okay, so what side length x means we're broke? Where are we broke in this scenario? We're at 0 over here, right? I can solve this equation, x squared plus 1 equals 0. So that means x equals minus 1. But wait a minute, if I plot this thing, if I look at the whole thing, where is it crossing the x-axis? So that's the x-axis there. Where this crosses the x-axis, it's 0. Where does it cross the x-axis? It's okay, we can do this. Right, so we got the white line, we got the red line. Where do the white lines and the red lines meet? They don't. Well, wait a minute, I solved it. Let's see, x squared plus 1 equals 0, x equals minus 1. That's because I took x equals minus 1 and they were squared, so I took square roots, and I get x equals minus 1. Is that right? At x equals minus 1, is it none? Do they meet? No, because I lied to you. This is wrong, right? Right? People who work with math, you probably just like, yeah, you totally cheated there. Right? That's not right. I basically said the square of 1 is minus 1, or square of negative 1 is negative 1. That's what I did. I pulled a fast one on you, right? It's easy to lie with mathematics if you're fast enough, right? So looking again at what these sign things do, positive times positive gives me a positive, negative times negative gives me a positive. I have to have mixed signs to get a negative. This statement is asking, what number can I multiply by itself and get a negative? Let's see, let's try it. Plus 1 and plus 1, no, that's plus 1. Minus 1 and minus 1, no, that's plus 1. 2, 2 times 2 is 4. Okay, what about minus 2 times minus 2? 4. Dang it, they're not negative. What do we do? What square has a negative area? That's basically what it's asking, right? This little problem was an issue for centuries. And I'm sure you guys lost a lot of sleep about that, didn't you? Oh my gosh, what do we do about that? Let's see if I get on the right page. This is asking what number can you multiply by itself and get a negative. Given those rules, you can't do it. It's because it relates to areas. There's no such thing as a negative area. Right? Does that make any sense? It's just like a negative length. It doesn't make sense. In a way, this is like looking through a looking glass. This number is saying there's an alien world attached to this statement, and it's going to freak you out. Right? Just step through the looking glass. This thing was bumped into until about the 1700s, because the idea of a number producing a negative area just didn't make sense. Right? No known number can satisfy that. So just maybe a little bit of history of numbers. I like pie. So sometimes I'll have a pie, or 2 pies, or 3 pies for lunch. But sometimes I don't have a pie, so I borrow a pie from someone. Then I'm in debt, and I have a negative pie. Right? And so sometimes we share pies, and we cut pies into fourths or quarters or 2/3. And so we have ratios of pies, fractions of pie. And also pi is just neat, 3.14159. Now I'm feeling very fine. Thanks for laughing. Right? So we have different kinds of numbers. Numbers have grown over the centuries, right? Negative numbers weren't accepted until the 1700s. Sure, we had fractions at some point, because I'm sure plenty of Greek Athenian soldiers were splitting pies. This fills in the rest of the real number line, where we have irrational numbers that cannot be represented by simple fractions, 1/2, etc., like square root of 2, pi. Those are irrational numbers. So as we've lived through the centuries and the millennia, and more numbers have been needed, oh, I owe you a pi, so we have to invent a whole number to deal with it. We expand the number system. So what do you think happened with this one? In order to deal with this, right, no real number solves this. Because you can't get some number out of all this that satisfies that and this. So we need a number multiplied by itself gives a negative. So what do you think? Maybe we need more numbers. Any takers? Yes, there are more numbers than that. No, you're crazy. Go away. How many vote Shawn's crazy? You guys are very kind. Right? So yes, we need a visitation from another world. So let's just call it some number that we multiply by itself and we get a negative. Right? Just call it just I. Let's call it I squared. Okay, so that means this is an imaginary number. It lives only in your imagination, as ridiculed by Descartes. These are not real, these are imaginary, there is no such beast. Right? What number can possibly do this, given all the numbers that you know in the real number system? Until a surveyor, a Dutch fellow in the 18th century, he came along and he looked at things a little bit differently. So let's go back to this basic stuff. Come on, stick with me. Come on. We could do this. We could do this. More maths. Are you guys ready? I'm getting some interesting looks from people. You brought me out for this? Okay. 1 times 1 is 1. Most of us learned this stuff in primary school, but you don't quite see it this way. Wessel imagined this a little bit differently. Imagine +1 and -1 on this number line. He imagined these multiplications for signs as additions of angles. So think of +1 as sitting at 0 degrees, 360 degrees. Think of -1 sitting at 180 degrees over here. Right? If we multiply 1 times 1, it's like adding 360 degrees. Just a full rotation. So 1 corresponds to 0 degrees. Multiplying by 1 corresponds to adding a whole rotation. So we end up at 360. So how do we get to -1? What's the trick? Maybe if we have 1 times -1, this is an addition of how many degrees? 180. So we start off at 1, right? 1. We add 180 degrees. We're at what? We're at 180 degrees, which is -1. It's looking at things a little different. Right? Okay, so how do I get back to 1 if I'm at -1? How many degrees do I add? Right, so I just keep going to continue the rotations. So 180 degrees plus 180 degrees is going to get me to 360, or -1 times -1 is 1. So how many of you have seen this presentation of sines, right? Not a lot of people, which usually they just tell you this bit, but they don't illustrate how it connects to some of these interesting rotations. Okay, so let me throw a curveball at you, in addition to all the others. Okay, what happens if I rotate 90 degrees? I'm up there. What number is that? Well, on the real number line, it's 0, but you're not at 0, you're up here. So if you're just looking at the reals, it's 0. But actually, let's call that I. Ha ha! Right? So 1 times I gives me I. In other words, 1 at 0 degrees plus 90 degrees sticks me 90 degrees outside of the real number system. So lo and behold, what happens if I add another 90 degrees? Where am I going to be? I'll be at -1. So that is I times I is -1. I squared equals -1. That was the beginning of all this stuff. Imaginary number, some crazy number that you multiply by itself and you get -1. You can continue the process, right? So you can say go another 90 degrees, we're going to get to -I. You can add another 90 degrees and you get back to +1. So that's just a very different way of looking at something that you're probably very familiar with, those multiplications of signs. You guys ready for the pop quiz? Yes? So along this line here, we have the real number system. +1, -1. No crazy Cheshire cat things poking their heads in. But along this, that's where the Cheshire cat lives. Along the direction of these imaginary numbers. These are imaginary, they are not real. But so look what happens to this original little problem. We can now figure out the answer to this thing, right? Where does this cross the x-axis? What's the solution to this? What x solves this? And in order to solve it, you have to look at it from a larger view and recognize that reals are part of a larger number system. And actually, that curve does indeed intersect the x-axis. It's just in order to do so, you have to extend the number system out into another dimension. We live in a real number system. That's what's familiar to us. But it's actually embedded, it's a smaller part of another dimension of numbers, the complex. How does that make you feel? All this time above your head, there's an imaginary number. Oh, what's it doing? It's following me around. Who cares? Yeah, so what? Right? Why should you care about this? Right. Well, as I understand mathematicians, right? Yay! Right? So you no longer have unsolvable little algebra problems. You're not running into this x equals square root of -1. What the heck do we do with that? Right? There's no hidden door of like forbidden numbers. If you go through that door, you'll never get money to do your PhD kind of thing. Right? Because science is the noble pursuit of funding. Right. Now numbers are considered complete, at least within the sense of algebra. So complex numbers allows you to, as you saw, extend out these functions, and you can get roots for any equation into a higher dimension. So there's this thing called the fundamental theorem of algebra that says any nth order polynomial has n roots. Some of them may be complex and in another dimension. Did you get all that? Okay, sweet. Right. Okay, so once again, though, as Descartes said, these are not real, they are imaginary. What are these beasts that you speak of? What are they? Who cares? Does anyone else care? Mathematics ought to be viewed as an ever-expanding mansion in space, with new links constantly growing between previously separated compartments. Recall the fictional view of mathematics. Mathematical objects are inventions, fictions that have no existence in and of themselves. And this resonates with describing maths as a language, right? Mathematics is a product of human imagination grounded in our experience with the world, like real numbers. It functions like a language, but it leads to these oddball alien things, imaginary numbers, complex. Although math has some utility, right? It appears also to have strange things perhaps only appreciated by its practitioners. For instance, evolution may be alleged to create our ability to do math, but the emergence of gifted mathematicians, may be akin to, say, gifted artists, right? Only the artists can really appreciate the art they make. That is until they die, and then it becomes very valuable, right? But I don't know too many mathematicians that are dead that their lithographs got really expensive. Can you imagine if Newton had patented calculus? Oh my gosh, how much money would we owe the Newtons? But completing this number system and dealing with these annoyances, like there's no way to solve this x equals square root of -1. There has to be a way to solve this. Such completion is partly driven by an artistic appreciation. A mathematician, like a painter or poet, is a maker of patterns. The mathematician's patterns, like the painters or the poets, must be beautiful. Beauty is the first test. There is no permanent place in the world for ugly mathematics. So not too long ago, there was a beauty pageant. A survey in an issue of Mathematical Intelligencer asked readers to rank mathematical theorems in order of not their usefulness, not their accuracy, not their simplicity, but their beauty. What do you guys think of that? What? There's beauty in math? Right? Once again, so these crazy mathematicians, oh, this formula, beautiful. Right? Does that seem odd to you? Beauty's in the eye of the beholder, right? Any takers on what one? This one. So some of you may recognize Euler's formula, right? This formula won not because, oh, that E is shaped lovely. Oh, the balance of the figures and the form. No, it's because it relates fundamental constants of the universe, the imaginary number, and two foundational constants all together into one expression. This is actually a fairly profound mathematical statement. Unless you're a mathematician, you may not appreciate it. And I can understand if you're not going, yeah, I would have picked that one too. Right? So we have imaginary numbers winning a beauty pageant. But once again, can we answer Descartes' question? These are not real, they are imaginary. What are these beasts you speak of? Right? What's the connection? Consider again the evolution of maths. The categories and modes of perception of man's cognitive apparatus are the natural products of phylogeny and thus adapted to the parameters of external reality in the same way and for the same reason that the horse's hooves are adapted to the prairie or the fish's fins to the water. It's no different than having a beak that's really good at extracting nectar or cracking nuts or hammering students' heads. So it's purely a practical ability. Only things that are useful survive natural selection. The logical structure of the universe allegedly guided evolution to man's logical ability. Logical schemes in the coordination of actions, cause and effects, along with physical realities, gravity, inertia, friction, are equated with logical deductive powers. Such abilities apparently include aesthetic appreciation for fictional entities. Somehow natural selection operated on these abilities during periods of latency, and such fictions result in strange entities disconnected from reality. Well, I guess I need a drink of water now. And we could end the story there. Do you think I'm gonna? I still got 20 minutes. And I've got quite a bit more water, so it really goes on. And you guys want to do some more maths, we can always do that. But how about I just show you an equation? It's the Schrodinger's equation. You may or may not recognize this. Maybe something that you woke up this morning and was floating in your mind, emblazoned in figures of fire. Schrodinger's equation, yeah. Right. Solution to Schrodinger's equation describes not only molecular, atomic, and subatomic systems, but also macroscopic systems, possibly even the whole universe. Yeah, that's Wikipedia being a bit over the top. But look what's in there. Yeah, ding. Hear the bell ring. We've got Planck's constant, just a constant. And behold, we have I. Imagine that. These are not real, they are imaginary. What are these beasts that you speak of? This equation is rather profound. Experimental confirmations of this equation are to extreme precision. There's a profound connection between the art of mathematics and reality. Maths people led to complete the number system so they could feel better about not forbidden numbers, etc. Ends up being a key aspect in a description of fundamental reality. It's very strange that mathematicians are led by their sense of mathematical beauty to develop formal structures that physicists only later find useful, even where the mathematician had no such goal in mind. Physicists generally find the ability of mathematicians to anticipate the mathematics needed in the theories of physics quite uncanny. It's as if Neil Armstrong in 1969, when he first set foot on the surface of the moon, had found in the lunar dust the footsteps of Jules Verne. Imagine that. It's kind of eerie, don't you think? It's kind of weird. It's like a visitation from another world. And it's this connection that causes so many problems for philosophers studying this stuff, trying to understand what does it mean. These issues have not gone unnoticed for a long time. Wigner, he gave a lecture in 1959 and published a paper called The Unreasonable Effectiveness of Mathematics. Why would these mathematical oddities and castles in the air connect to reality? What does this say about the fictionalism idea? It's just a bunch of inventions. Are these all just figments of our logical imagination? You know, many mathematicians are not fictionalists. These connections in the mathematical objects inspire belief in their existence. Many mathematicians believe that numbers, equations, perfect circles, and so on exist in some ideal abstract sense. I've been around a lot of mathematicians, a lot of them a heck of a lot smarter than me, and very few of them are atheists, except for the Russians. Boy, the Russians are just full-on atheists. I could go on. I think it's because they're properly trained by an atheistic society. But many mathematicians that I've known over the years, they marvel at these eerie connections between completely disconnected and disjoint branches of mathematics. And what do they see? They see the fingerprints of something divine. And so what do some of these objects have, in a sense, if they're real? If they're real, shouldn't they have some connection to reality, so that if I could, by some bizarre happenstance, if I went around with an eraser and a shotgun and I destroyed the imaginary number I have no idea how I would do that. It's a lot of erasing, right, in people's heads. Maybe it's like the Men in Black thing. You could use the Men in Black thing. Forget about I, ding. Go around and destroy I. Would I destroy the universe? Would I trigger a supernova in the mathematical abstract world that would ripple through reality and give you a really nasty headache? Would it change the reality, right? Is there a causal connection between these things? It makes me think of that statement, the map and the territory are different, right? You've got a description of an area, but then you've got the area itself, right? A red rose is still red if I call it blue. The description is just no longer true. Erasing all the results for the Pythagorean theorem throughout history won't change the fact of the relationship a squared plus b squared equals c squared. We just might see it differently. It might have a different name. The theorem of PowerPoint animations, right? Yeah, I like that name, don't you? Yeah. Of course, this problem was grappled with by a philosopher of many philosophers, Frege, who stated that these laws of number are not really applicable to external things. They're not laws of nature. They are, however, applicable to judgments holding good of things in the external world. In other words, they're the laws of nature. They're the architecture for reality. Scientific laws we've encountered, characterized, codified, are structured and describable in mathematical terms. The fact that the universe obeys mathematical laws has not been lost on many astute observers over the centuries. Philosophy is written in this grand book, The Universe. It's written in the language of mathematics. Its characters are triangles, circles, other geometric figures. And the power that it gives us. I find it amazing that it's possible to predict what will happen by mathematics, which is simply following the rules, which really have nothing to do with the original thing. Richard Feynman, big shot 20th century theoretical physicist. Evolutionists typically claim that our logical capability evolved as a result of the logic in the world, and others, many others, find it quite unlikely. A great mathematician fully, almost ruthlessly, exploits the domain of permissible reasoning and skirts the impermissible. That his recklessness does not lead him into a morass of contradictions is a miracle in and of itself. Certainly, it's hard to believe that our reasoning power was brought by Darwin's process of natural selection to the perfection which it seems to possess. Remember Bob? Bob the mathematician, right? What sort of survival skill set does he have? Just don't let him drive, I guess, right? Indeed, we have an intuitive sense about the way the world works, but our logic leads us into the counterintuitive that we in fact reject. Haha, gotcha. Negative numbers, complex numbers. How many bizarre mathematical constructs have emerged from mathematicians that were just imaginary, with all these beasts that turn out to be intimately related to the universe? The profound interplay between the workings of the natural world and the laws of sensitivity of thought, an interplay which, as knowledge and understanding increase, must surely ultimately reveal a deeper interdependence of the one on the other, our minds and reality. Evolutionists would have us believe there's no preordained, predetermined mathematical truth out there. I'd say there's a bit of truth to this. Context is very important. Negative numbers were rejected without proper context. But apparently other truths are context independent. Pythagorean theorems. The universality of mathematics is suggested by the fact that mathematicians widely separated in space, time, culture find the same mathematical theorems and ideas. Bertrand Russell, certainly no friend of theism, concluded from his study of the history of Greek philosophy that mathematics is the chief source of the belief in the eternal and exact truth, as well as in a supersensible, intelligible world that are all distinctly mathematical. Some of these mathematical objects, of course, are counterintuitive. Some hinge on mathematical objects we would reject. Some are completely removed from our everyday experience. And some are darn ugly. Does anyone disagree? Do you think that's pretty? Can I get you to write a review of my paper and send it in? Said, this is pretty. I like this. What does this say about their connection to truth and reality, right? Just this impression, this is ugly. Right? I think it's because we have a predilection for simple solutions. Okay, say I want to light a candle. And I decide I'm going to construct a device that lights the candle, but supposedly in an amusing way that eventually will get there, right? It does light the candle. Look, I lit the candle. Isn't that, oh, that's lovely. Every time I want to light a candle, we have to shift over this whole table filled with all these nifty toys and light a candle. Does that sound simple and elegant to you? No, I think we just light a match. Right? Simple and elegant, convoluted, ugly. Right? In fact, simplicity is used as a guide for finding mathematical truths. One of the most important things in this theoretical physics business to know when you are right. It's possible to know, way ahead of checking all the consequences, you can recognize truth by its beauty and simplicity. Feynman again. Here we see a renowned theoretical physicist equate truth with aesthetics. What a lovely donut. It must be true. Can anyone doubt the truth of donuts? It's Sunday afternoon. Thanks for sticking it out with me. I can see some of you are really hanging in there. Okay. Also, I can tell you're struggling because you didn't laugh at my brilliant humor. All right. These instincts of Feynman's, right? It's not an accident, right? When you're doing theoretical physics for 20, 30 years, you tend to develop an instinct for if you're onto the right path. I'm onto something, right? It's not an accident. And he's by no means the only one. I was thus led to a long calculation, the longest in my career. Full of local, tactical tricks, the calculation proceeded by twists and turns. There were many obstructions. But always after a few days, a new trick was somehow found that pointed to a new path. The trouble was that I soon felt I was in a maze. I'm not sure whether, in fact, after so many turns, I was anywhere nearer the goal than when I began. This kind of strategic overview was depressing. Several times I almost gave up. But each time, something drew me back, usually a new tactical trick that brightened the scene, even though only locally. Finally, after about 6 months of work off and on, all the pieces suddenly fitted together, producing miraculous cancellations, and I was staring at the amazing, simple final result. That's the description by Chen-Ning Yang on his derivation that won him the Nobel Prize in physics. I've had a taste of that. They haven't given me the Nobel Prize yet.
Feels right.
Oh yeah, it feels, yeah, for mathematicians. Yeah, there's a whole story to that. But I had a taste of that. When I did my master's, I was doing real maths. And some of the derivations that I did were insane. It's pages and pages and pages. This is crazy. Is this ever going to end? And then you would start seeing terms canceling. Bang, 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 bang. I'm onto something. And out would pop this lovely, simple result. And run to the, hey, did you get this too? Yeah, I did it. Oh man, this is awesome. Hey, did you get this result? Yeah, this was awesome. You see it. You see it happen. It tends to lead you in that direction. And you appreciate the simplicity of it all. It is clear that Yang's confidence in his calculation is bolstered by the miraculous cancellations he experiences. But such thinking is obviously anthropocentric, very human-centered, and perhaps even childlike. What has miraculous simplification of the notation we use in describing nature got to do with nature itself? Those representations of biological mechanisms are typically quite ugly. I just have to share with you a lovely movie. There's really no Schrodinger equation for mathematical biology. Some of you may have seen this stuff. This is the Mandelbrot set. Out of a very simple relationship using complex numbers. You start with a complex number, you square it, you add a number, it pops out. Then you do it again. You square it, you add a number, it pops out. You just keep doing this again and again and again, and you get fantastic complexity. These patterns that just go on and on and on from such a simple representation. These patterns are found in biological systems all over, from your arterial distributions of your vasculature to the leaf patterns, to also fjords and whatnot. And as you dig deeper and deeper into these systems, you start where you began. You go back to where you started from. Fantastic complexity from such simple little devices, a simple little equation. And we see this all over the place in nature. These complex patterns that are aesthetically pleasing are generated. Anybody heard of Fibonacci? The Fibonacci sequence? It's intimately related to the golden ratio, an aesthetic ratio that we see exploited by architects and artists all over the place. Universal facts keep emerging about reality. Schrodinger's equation, Newton's law of force, Einstein's energy equation, electricity and magnetism related, Maxwell. What's this one? Pythagorean. No, it's the theorem of PowerPoint animations. Get it right. Right, so we have the most beautiful formula, according to mathematicians. We have the Mandelbrot set, and we have this one. Tyler, what is it? Oh, crud, I have to wake up. Anyone want to help Tyler? What is this one? The quadratic equation. Does that trigger any memories? Oh, the quadratic equation. Right, yeah. Has anyone ever used a piece of software they don't have the manual to and found it fun? This is fun. This is fun. How do I get from point A to point B in this stupid piece of software? Okay, when I was at Sandia Labs, I was doing all these fancy simulations of big fancy computers, but they're no good unless you can actually see the result. So I was using a visualizer that went through three-dimensional simulations, and you could make pretty pictures and stuff. But the built in-house software that I was using had no manual. There's no manual. But so the way I survived is I just asked, hey, I want to blah, blah, how do I do this? Oh, I just push this button and push that thing, okay, sweet. And then I was, hey, how do I get this there? Oh, I just do this, okay, sweet. And eventually I exhausted the knowledge around me. And then someone said, oh, look, there's a button that says help. Oh, help! Wow, great, I push on help. What do you think happened?
Useless.
Yeah, it popped up this little message box and it said, are you kidding? You want help? I'm gonna write documentation, you're insane. Right? So I abandoned that software and I went on to professional software so I could do my job. Yeah, that was loads of fun. Well, what's the presumption when you're trying to figure out a piece of software or you're trying to fix something, fix a car, whatever? There's a logic to it, right? Okay, I assume this piece of software was not designed to torture me. It's actually supposed to do what it says it does, and so I can get there, right? So I push the right buttons and I put the right things in. Anyone worked on a car? It's like, this was built by a madman. There's just no sense, no logic to it, right? That's because you assume that there's a logic to things. And so we assume the same thing. There's a logic to building stuff, right? We base a lot of that, right? And there's an artistic element. It's this artistic element, right? Very practical, very aesthetic. We've encountered fundamental relationships, intimate relationships in the fabric of reality from a seemingly alien world that's intimately related to everything. So I ask you, why? Why? So a lot of very smart people have wrangled with this over the years. And there's a Christian apologist, William Lane Craig, and he summarized some of this. Talking about the realist perspective that mathematical entities are real in their own abstract reality. You have two different views. You have a non-theist or an atheist. No God, there's no God. As a philosopher of mathematics, Mary Lane points out, for the non-theistic realist, that mathematics exists in some abstract way. The fact that physical reality behaves in line with the dictates of a-causal mathematical entities existing beyond space and time is a happy coincidence. Yay! I like happy coincidences. Anyway, did that seem too mocking? Sorry. For the theist, by contrast, the theist, realist, can argue that God has fashioned the world on the structure of mathematical objects. This is essentially what Plato believed. The world has mathematical structure as a result because God made it that way. So for a fictionalist, mathematics is just a bunch of inventions. The non-theist, Lang says that on anti-realism, relations amongst mathematical objects just mirror the relations amongst the things in the world. So there's no happy coincidence. Oh. Well, that's fine and dandy, but what remains wanting is an explanation why. Why does the physical world exhibit such a complex and stunning mathematical structure in the first place? How handy is that? The theist. The world exhibits a mathematical structure it does because God has chosen to create it according to the abstract model he had in mind. This was the view of the Jewish philosopher Philo of Alexandria, who maintained that God created the physical world on the mental model in his mind. Mystery. Why bother? Well, it's mystery. It's intriguing. I'm curious. Why? The world of H.P. Lovecraft, the themes in his works were typically woven around forbidden, dark, esoterically veiled knowledge. Many of his characters are driven by curiosity, scientific endeavor, and in many of his stories, the knowledge they uncover proves Promethean in nature, filling the seeker with regret for what they have learned, destroying them psychologically, or completely destroying the person who has the knowledge. Lovecraft believed in a purposeless, senseless, mechanical, uncaring universe. Human beings with their limited faculties could never fully understand this universe, and the cognitive dissonance caused by this revelation led to insanity, in his view. At the center of the Lovecraftian universe is the god Azathoth, a god of chaos and disorder and madness. And if man was to see creation in all its power and glory, he would be driven insane. That's the world of H.P. Lovecraft. But we don't see that. We see something else. You find it strange that I find the comprehensibility of the world as a miracle or an eternal mystery. Well, a priori, fundamentally, one should expect a chaotic world which cannot be grasped by the mind in any way. The kind of order created by Newton's theory of gravitation, for example, is wholly different. Even if man proposes the axioms of the theory, the success of such a project presupposes a high degree of ordering of the objective world. That is the miracle that is constantly being reinforced as our knowledge expands. Look at all the order in this universe. Did I just terrify someone? One of the most important things in this theoretical physics business is to know when you're right. It's possible to know way ahead of checking all the consequences. You can recognize truth by its beauty and simplicity. We see a user-friendly universe. Guided by a human sense of beauty and simplicity, we find truths. Truths accessible via totally counterintuitive mathematical objects. They are imaginary, they are not real. Rejected by a sense of logic in a world we live in. Has Feynman answered Pilate's question, what is truth? So I'm going to shock everyone and say, guess what? I'm a Christian. I'm a theist, right? So I see mathematical objects reflect their simple embedding within truth. This truth itself is a causal agent. Truth. I am the way and the truth and the life. We are made in the image of a God with this mental capacity for mathematical reasoning, and we are imparted with the shadow of that ability. We have this capacity for mathematical reasoning, permitting us to explore a rationally intelligible universe. That's why, in my opinion. Math is a language. It describes relationships, quantities in the world precisely. It's a game, like chess, with formalized rules. It's related to the intrinsic architecture of the universe, sometimes in bizarre, completely unexpected ways. It's a distinctly human endeavor. Things like aesthetics and beauty inspire one to find remarkable things. And it's a mystery with a simple and divine solution. And so I am New Mexican, so as all good New Mexicans, I have to show you a picture of New Mexican food to torture you at the end. Right. So this is Sandia Crest, the Sandy Mountains in Albuquerque where I grew up. And so that was one of my favorite restaurants. So maybe some of us want to go eat now and go enjoy the rest of our afternoon. I see the sun came out. And so now you can go off and you can practice multiplying imaginary numbers. Thanks for coming, guys.